Greetings. So today I will give you some intro to game theory. Because it turns out that it's a very handy tool to analyze optimal randomized online algorithms, possible competitive ratios. So in game theory, we will be dealing with so-called matrix games. Now in a matrix game, we have a coast matrix. This is usually denoted by C, and is just an array, a rectangular array of real numbers. So we can write this as it contains real numbers and it has n rows and m columns. Like for example, we can choose, say, a matrix having 3 rows and 3 columns, like 0, -1, -2, and 1, 0, -1, and 2, 1, 0, right? Now in game theory there are many possible ways to define games, but in our setting, which will be interesting for studying the online algorithms, there will be two players. One of the players, say A, chooses a row. So she is the row player, and generally A is a female player and B is a male player, or vice versa, just to make them differentiable a little bit, but it doesn't really matter. So since in Hungary it's we don't really have these pronouns of for male and female objects, players, and whatsoever, I think for this talk I will stick for male pronouns most of the time. So A chooses a row and B chooses a column. So for example, if A chooses like the third row and B chooses the second column, then the so-called the outcome of the game will be -1, right? So one of the players chooses the row, the other player chooses the column, and the coast is written in the corresponding entry. Now the aims are A wants to maximize the number, while B wants to minimize. The value, which is usually denoted as Cij. So this is the entry of the C, of the matrix C, in the ith row and j's column. Okay, so back to our example. For this example, we can have a number of strategies, but for example, if you just consider the choice of A. Now, player A either chooses this row or chooses that row, but if you see it, -1 is larger than -2, 0 is larger than -1. 1 is larger than 0, so it doesn't matter which column will player B choose. By the way, they are choosing the row and the column simultaneously, so independently and simultaneously, not knowing the other player's choice, they are just choosing the row and the column. all by themselves. So there is not, it's not really a wise decision for player A to choose the row 3, because row 2 always give you a better outcome. So since, for example, since row 2 is larger than row 1, and here larger means on each coordinate, row 2 is larger than row 3, sorry, yeah, okay, on each chord, so A should not pick row 3. And actually it's also true that row 1 is also larger than row 2, so A shouldn't pick A shouldn't pick row 2 as well. So here 0 is better for player A, then -1, 1 is better, and 2 is better than 1 because A wants to maximize. So player A is the one trying to maximize the number, the value of the game, and the second player, player B, wants to minimize the game of the value of the game. So basically we just show that no matter what, but A will choose the first row if player A plays in a sane way, in a rational way. Similarly, we have this player 2. Alright, now we see that the third column is pointwise larger than the second one, because 2 is larger than 1, 1 is larger than 0, and 0 is larger than -1, and player B wants to minimize the entries, so player B won't choose the third, and player B won't choose the second column as well, because it's also larger than the first one. So player B should choose the first column in order to minimize the value, which means that in this case both players have a unique strategy and the outcome will be 0 according to this optimal strategy. Now if any of them plays differently, then it will be worse for that player in question. So for example, if player B decides, okay, I'm not choosing column 1 but I will choose column 1, then if player A doesn't change, then B will get a worse payoff because player B wants to minimize. And also the switching to the third column is also a bad move for player B. And similarly, if player A just changes to the second or third row, then the gain of player A will be smaller since player A wants to maximize the value. Now, so it means that for an optimal strategy, player A have to choose the first row and player B has to choose the first column. Now the reason is that because A always can ensure the maximum of the minimum of the rows. Because if player A picks this row, so usually I ranges over the rows and J ranges over the columns. So if A picks the third row, say, then the worst possible scenario is the minimum of the row, which is -2. If player A chooses the second row, then the minimum of this row is -1. And if player A chooses the third row, the first row, then the minimum of this row is 0. So that's written here. And then it means that if player A chooses the best row amongst these guys, so the first one, then player A will ensure that the game's value is either this or even larger. So that's what I mean. That's what I mean by ensuring something. And usually B can ensure always, well, for each possible column. So for example, for column 1, the maximum of the minimum for j's and the maximum for i's, because if I choose the jth column, then the worst possible scenario for player B is that when player A picks the row maximizing the value of the entry they chose. So in general, if I choose one specific column J, then the worst possible outcome is maximum of these values in the column. So if I just compute this expression for each column, then the best I can hope, well, best I can surely achieve is just the minimum of these guys, because player B wants to minimize. Now, this means that if both players play in a good way, then, well, what can happen? So if it happens to be the case, if the maximum of the minima is the same as the minimum of the maximum, so if this happens to hold for a matrix, then this is the value, this is the outcome of the game, the definitive outcome of the game, if both players play rationally. So if they play according to some winning or optimum strategy. So this is the value of the game if both players play, well, optimally. Now, in general, this is not usually the case. So, for example, let's see another example. But so if I have another cost matrix, say 1, -1, -1, and 1. So if I just compute the maximum of the minimum, Cij, so what's that? I have to compute the minimum of each row. This is -1 and this is -1, and the maximum of these values, now this will be -1. While the minimum of the maximum, Cij, so the maximum of each row is 1 here and 1 there, and the minimum of these two guys is 1. Now these two are not the same. This means that there is no optimal strategy for any of the players picking only one column, because, for example, if in this case player 1 just picks this guy, the first row, then of course if player 2, player B, knows that player 1 chooses the first row, then of course player B should choose this column. But if player A knows that player B will choose the second column, then player A should switch, because by the switch the game value just increases, which is good for player A because player A was to maximize. But then if player B knows that player A will choose the second row, then player B will choose the first column because the game value decreases, which is exactly what player B wants. And then player A again changes, and then player B again changes, and so on. And this can just be repeated an infinite number of times if you wish, and it will oscillate. So it's not a definitive strategy for any of them. So you can't say that it's best to pick this, because if the other guy knows what you pick, then he or she will get a good counter strategy. That's why usually, so these games are called pure games. Pure means choose one row and column. And there is an option for playing in a randomized way, a mixed game. It means that you are just choosing probabilities for each row, or for each column if you are player B. So player A who previously chose one row, player A chooses a distribution, a probability distribution over the rows. So it's just a vector P, which is just P1, P2, and so on. Pn, since we have n rows. And of course, the distribution means that the sum of these Pi's is 1. And of course, each Pi is somewhere between 0 and 1. So that's what makes it a distribution over these rows. And player B chooses the distribution over the columns. So player B, so essentially they are choosing a randomized choice. Player B chooses also distribution. Now the distributions are chosen again independently at the same time, Q2, so they don't know the other player's distribution. And again, of course, the sum of the Q's is 1 and each Q is non-negative. Now if player A picks row I with a probability of Pi, and player B picks the jth column with a probability of Qj, then it can be shown that the expected value of the game it's just because they are picking these independently. This means that it means that choosing entry, the entry ij, it has a probability of Pi times Qj, because in order to pick this particular entry, player A has to pick the ith row and player B has to pick the jth column. And since these choices, these moves are carried out independently, it means that we have to multiply the probabilities, and has a value of Cij, of course. So it's just the entry, the corresponding entry in the matrix, which means that the expected value is just the sum of I from 1 to n and the sum of j from 1 to m, Pi times Qj times Cij. And of course, if you are familiar with linear algebra, you know that it is the same thing as multiplying the vector P by the matrix C and then by the transpose of this vector Q. So for example, if we have a game exactly like this, so let's just compute this once. So for example, if the coast matrix is 1, -1, -1, 1, and A chooses the probability vector of, say, 1/4, 3/4, it means that player A will choose the first row with a probability of 1/4 and row 2 with a probability of 3/4. And say the other player, player B, has another strategy which is just like, say, 3/4, 1/4. Why not? Then it means that if you just compute this with this formula, then the expectation is, what is the expectation? So it's just the first row is 1/4 times the first column is 3/4, and in this case we are picking this guy there. So we have 3/16 probability of having the value of 1 plus 1/4 times 1/4 times -1, because that's the probability for choosing the first row, that's the probability of choosing the second column, and here we have this -1 there, plus the same for the second row, which is governed by this 3/4 times 3/4, so it's just the first column times -1, plus the last one is just 3/4 times 1/4 times 1. Yeah, but this is the same, so if you just compute this, it's like 3/16 minus 1/16 minus 9/16 plus 3/16, which is, well, it's around -1, or I'm not entirely sure, because it's just adding numbers, so it's 3 plus 3 is 6, minus 10 is essentially -4/16, which is -1/4. So as an expected value, if player A chooses the rows according to this probability and player B chooses according to that probabilities, then the expectation of the outcome is -1/4. But this is the very same figure which you get if you just multiply as vectors and matrices this guy here, which is the P, times the coast vector, coast matrix, which was 1, -1, -1, 1, and then you just multiply the transpose of Q, so it's just the first entry will be the first entry, but this time we are just writing down the vector in a vertical way. That's what transposition means. So the product of these things is 1/4 times 1 plus 3/4 times -1, which is just 1/4 minus 3/4, that's -2/4, that's -1/2. And then for the other we have 1/2, because it's -1/4 plus 3/4. Okay, and then we get -1/2 times 3/4, which is -3/8, plus 1/8, which is -2/8, which is still -1/4. So it's -1/4. This is the same. So this is how we usually should compute the expected value of the game if the players play according to some specific strategies. Now you see that it's it's not the best choice for player B, again, because it was just an example. So it says that because if A chooses this specific probability vector, this specific distribution. Then, and player B knows it, then player B knows that after multiplying P with C, it will end up by this vector. And now I want, as player B, as I want to construct a probability vector which minimizes the dot product of these two vectors. And of course, because minus 1/2 is the minimum value of this vector, so since minus 1/2 is the minimum of this vector, now where am I? Yeah. So since minus 1/2 is the minimum of this vector, it makes sense to choose always the first row. And if player A plays according to this strategy written there, then an optimal counter strategy is a pure one for player B. And this is always the same thing. So an optimal strategy is against some possibly mixed strategy. There is always at least one optimal counter strategy, which is a pure strategy. You only have to choose the minimum value if you are trying to create the counter strategy for player B. And similarly, if player A knows that player B will choose according to this probability, then player A just have to multiply the matrix with the vector, and player A will get something like it's 3/4 minus 1/4, which is 1/2. That's right. And then the other position is minus 1/2. So if player A knows that the strategy of player B is this one, then player A can design a counter strategy which is just simply choosing 1/0, which is just choosing the first row, in which case player A will ensure that it's 1/2. Yeah, it's great, and it's in general true. So you just have to, if you are not just designing a strategy for player A, then you just have to, against some fixed strategy of B, then you just have to choose the maximum value of that vector. And if you are designing a counter strategy for player A, then you just have to compute the P times C, and just like we've seen before, and pick the minimum value. This is what's called the Loomis theorem. The Loomis theorem says that, say, the minimum, but in this case, the minimum player doesn't pick a specific column, but a distribution of the maximum of P. Now that's again what, so I'm just P times C times Q transposed. Now what does it mean? For each possible strategy of me, so it's just if I'm picking as player B, I'm picking a Q, then against my decision, this is the optimal counter strategy of player A, because this is what maximizes the P, C, Q, the expected value of the game. If I decide to stick to my probability vector Q, and in order to construct this optimal counter strategy against Q, so it's just the optimal counter strategy against Q. So it's enough just to think among the pure strategies, and this can be written as taking the maximum only on the row, only on the only on the rows. Now, of course, in the matrix notation, choosing the ith row is multiplying by the ith unit vector. As this should be familiar from linear algebra, so it's this E of I is just the 0, 0, 0, blah, 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 0, 1, 0, 0, 0 vector, and the 1 happens on the ith coordinate. So multiplying something, some other vector, some vertical vector with this, not column vector, with this ith unit vector will just choose the ith row of that column vector or matrix if you wish. So basically this means that for constructing an optimal counter strategy for some fixed against some fixed possibly mixed strategy of the other player, it's enough just to think about the pure strategies. This will be important when we will get to the application for online algorithms. And the other thing is the fundamental theorem of game theory. So the fundamental theorem of game theory says that there is always an optimal strategy if you are just thinking about mixed strategies. It says that if I want to maximize the P and minimize the Q, PCQT transposed, right? So this, as in the similar to the previous one, this is the value which player A can ensure. For each P, for each possible strategy, player A just calculates the worst possible scenario, which is this min Q, PCQT, and amongst of these guys, player A chooses the best one. But this will be the same as the other way around, so it's just the minimum of the maximum of P, C, Q, T. That's the same. It means, it says that if you are dealing with probability vectors, CQT, PCQT, if you are dealing with probability vectors, then you can replace the maximum and the minimum operators. This is the fundamental theorem of game theory. So there is always an optimal strategy. This is not the case as we've seen here, because there we are not considering all the possible distributions, probability distributions, only the pure ones. This can happen because amongst the pure ones there is not always a clear coincidence. But in the case of randomized choices, the case of stochastic choices, the case of distribution probability distributions, it's always the case. It's always holds. So it means that there is an optimal strategy, P star, Q star. Usually the optimal is denoted by star. P star, Q star exists. Now, for example, for this matrix 1, minus 1, minus 1, 1. So for this one, this stuff, if player A just chooses by 1/2, 1/2, then what happens? then we will get a 0 here and we will get a 0 there. So it means that it doesn't really matter what player B does, the value of the game will be 0, definitely. And similarly, if player B just picks the columns according to the very same distribution, 1/2 for the first column and 1/2 for the other column, then the value of the game will be 0, but against this particular strategy, player A cannot improve. So here it doesn't really matter what do we play, 0, 1, 1, 0, 1/3 or 2/3. The outcome will be always 0, 0 and 0. In general, the outcome will be always, at least as large as the minimum. Now, if we do this the other way around, so if player B picks this strategy, then the product of these two things, C and QT, will lead us into 0, 0 column vector, and then it doesn't matter what player A does, player A cannot improve anything, so the 1/2, 1/2 is at least as good as, say, 1/3, 2/3, because that's also making the product of 0, or 0, 1, that's also a possibility, but that will also give me 0, so it doesn't matter what to do. So if both players play according to 1/2, 1/2, then the other player, no player can switch to another strategy, and if they switch to another strategy, then there will be a better counter strategy for the other player. That's why the optimal strategy for both players is just to play 1/2, 1/2. And let's just as an exercise, let's just compute the optimal strategy for a somewhat more complicated matrix, just to get hang of it. So we can do an exercise. So exercise, determine the optimal strategies optimum strategies say for both players for the matrix, say C 2, 4, 5 and 3. Okay, so how we do this? First we are just writing the solution. So the optimal strategy, so by the fundamental theorem of game theory and the Loomis theorem, we just want to compute the minimum of the maxima of the product B, C, Q transposed, which is the same, according to the fundamental theorem of game theory, the maximum of the minima of the P, C, Q transposed. And by the Loomis theorem, it's just the same as the minimization of the maximization, but in this time I only have to deal with the unit vectors instead of arbitrary probability distributions. For the ith unit vector times C times Q transposed. And if we can compute the minimum of this expression, the place, the value of Q for which it gets the minimum, so the argument, if we call it this way, then we will determine as optimal solution for player 2, for player B. And similarly, this side can be simplified to the maximum finding of the minimum for J and B, C, jth unit vector transposed. Now it seems to be scary, but it's always the starting point for determining a finite games value, because here this guy C times Q transposed is, if we just write Q as say Q1, I'm just choosing Q, so Q transposed is just Q1 and Q2. There is a probability of choosing the first and there is a probability of choosing the second column. And of course, if I'm just using the fact that this is a probability distribution, I can always reduce the number of variables by 1, because we have this Q1 there and the 1 minus Q1 there. So this is the Q vector. With Q1 probability I'm choosing the first column, and with 1 minus Q1 probability I'm choosing the second column. And the C matrix is given. This is 2, 4, 5 and 3. And if I just multiply it with this vector, so I'm just computing this part of the expression. This is always how we do this. This will be 2 times Q1 plus 4 times 1 minus Q1, and for the other guy it will be 5 times Q1 plus 3 times 1 minus Q1. Yeah, that's great, because we can collect the Q1 terms, so it will be 4 minus 2Q1 and 3 plus 5 minus 3 is also 2Q1. Okay, now this is the part. Now the maximum of the ith column vector, so for example if I'm just multiplying this with 1, 0, then I will get this expression. If I'm multiplying this with 0, 1, and that's the power of the Loomis theorem, I don't have to use P1, P2 at this point. I just have to, it's enough to use the unit vectors, because multiplying by 0, 1 will give me this vector, and I have to choose the maximum of these values, which means that this expression here is just the maximum of two things, the maximum of 4 minus 2Q1 and 3 plus 2Q1. This is the maximum. And I have to minimize this part. So I have to choose a Q which minimizes the maximum, and we've seen such things before. Again, if I only have one variable, which happens to be a probability variable, so it's just Q1 between 0 and 1, then this guy here is just something like this, 4 minus 2Q1, and the other guy is just something like this, 3 plus 2Q1, and the maximum of these two functions is just this line here, that's the maximum, and then I have to minimize this thing which is exactly at this point. So in this case, when I have a 2 times 2 matrix, it's quite easy to minimize the maxima. In general, we are just choking up that linear programming solution, and we just feed it to some solver, but this says that 1 is 4Q1, which means that in this case Q1 is 1 over 4. Yeah, now this means that for the optimal strategy, we have that the optimal strategy for Q is just choose the first column by a probability of 1/4 and the other column, the second column, with a probability of 3/4. Now we can do the same for P. I'm just doing this in order to finish the exercise properly. So for the player A, we have to compute this part, the P times C, and again it's P1 and the 1 minus P1 because P2 is always 1 minus P1. And I have to multiply by this 2, 4, 5, 3. 5, 3. So this part is just, I'm just writing it here. So this guy here is 2P1 plus 5 times 1 minus P1. And the other guy is 4P1 plus 3 times 1 minus P1. And I just collected the terms as before. So it will be 2P1 minus 5, that will be something minus 3P1, and the something is 5. Cool. And then we have the 3 minus 3P1s plus 1P, so it's plus P1. Okay, and again multiplying it by AJ is either this entry or this entry, and taking the minimum of these things is just taking the minimum, and I'm just switching it to red. It's just taking the minimum of these two entries, 5 minus 3P1 and 3 plus P1, and I have to maximize the probability distribution, so essentially P1. And again, I can solve this in a graphical way because there are not too many variables, so 1 is definitely not too many. And then there is a line for 5 minus 3P1, there is line for 3 plus P1. These two lines actually meet, so it's okay. And then the minimum of these things is depicted here, and the maximum of these two things is there. So again, I just have to make these two things equal, which means that P1 equals 1/2. Because, yeah, so I'm just adding 3 P1s and subtracting 3 is just 2 equals 4 P1, if you wonder how this came out. Yeah. Which means that the optimal strategy for player A is just to choose by 1/2 and 1/2. Yeah. And any of the players should any of the players deviate from these strategies which we just computed, cannot help for the given player. In most cases it will just get things worse. And what's the thing is that the value of the game is just P times C times Q transpose for these particular entries. So that's essentially well, okay, so we can compute this guy times the cost matrix, which is 2, 4, 5, 3 times, sorry, this was the strategy of the other player. So this is just the strategy of P, because P will choose the rows, times 1/4, 3/4. And if we just compute this, then it's 2 and plus it's 7/2, and the other thing is again 7/2. and then we are just well, we can take the product, of course, but it will be 7/2 no matter what. So the value of the game, that's what it's called, is on average, in expected value is just the value of the game is 3.5, which is just 7/2. So this is how usually just a simple exercise is solved. And of course, if there are more rows than 2, or if there are more columns than 2, then of course you don't do this, because it's okay, it's easy to do for one particular variable. But in general, again, if I have to maximize a minimum of these expressions, then I can make a linear program for that. So in the general case, if you are solving with the computer, then you are just introducing a new variable. So 5 minus 3p1, the minimum of these guys is always smaller than them or equal to, and 3 plus p1 is just at least as the t. And of course you have to write explicitly that p1 is somewhere between 0 and 1, because it's a probability, and you have to maximize this t, maximize the t. And if you solve this system of inequalities and maximize the t's exactly in the same way as you are solving linear programs, then again you will get t equals 3.5 and p1 equals 1/2. So it's the same. So the optimal solution of this LP system is of course giving you the optimal strategy for one of the players. And of course in that case you don't have to use this p2 equals 1 minus p2 stuff. It's good enough if you just leave it by as p1 p2 and feed it to the solver, because the solver doesn't really care whether there is one more variable or not. So it's just n variables or n minus 1. It doesn't really matter if n or m is that large. It's large enough. Yeah. Okay, so that's how game theory is usually done. And in the next video we will see how it's related to the online algorithms theory. Till then, bye bye.